Alright, hey, welcome back. Part 4 of retro computing. So last time we looked at tool chains, and I showed you some of the tools that I've been using and a few scripts wrapped around the macro assembler and the object converter. And we did a little bit of assembly language programming, but today I just want to jump into a bunch of assembly language on the PDP 1170 and take a look at what this instruction set can do. And then we'll go on in another video to looking at some more of the hardware aspects of the system. But let's just do software today. So you know, you've got a programming reference card, which is a great quick reference if you want a reminder on different addressing modes, a list of instructions, and so on and so forth. There's also the processor handbook that I've mentioned in the other videos, and I went ahead and had a hard copy made at a fabulous print shop that charges, you know, a few pennies per page. And I was flipping through the PDF so much, and the PDF is not bookmarked and such, that it was worth just going ahead and getting a hard copy of this. So we'll be playing around with this today. So let's start with a really simple program. Let's just add up the numbers 1 through 10, right? So just do a straight little sum like this. And you know, our algorithm is really simple. We have an initial sum equals 0. We have an integer I equals 0. We increment I, add I to our sum. And then if I is not equal to 10, go back up here and do this again. And when we're all done, we should get the sum of the first 10 integers, which should be 55, which is decimal, so we'll see it in octal. We can do this in the spirit of, you know, a higher level language. To start with, we can make memory locations called sum and I and work with those directly. And the multiple addressing modes of this processor let us deal strictly with memory, but we can also work with registers. So let's go ahead and do a little bit of both. So I will pop up a window here and go into a work location, and I'll just call this sum1. Alright, so there's a few boilerplate things in the beginning. Tell my students that they should always put their name in their programs, so I got to put my name in there just to, you know, make good habits. I'm going to use an asect directive, which tells the assembler that I'm going to specify memory locations. I don't want stuff to move around in memory, so these are going to be absolute addresses, and I'm going to start at location 1000. And I'm just going to put a label here which says start, and I'm going to initialize my stack pointer, because if your stack pointer happens to drop below 400, you get what's called a red zone exception. So give the stack pointer a value, even though I'm not planning to do any function calls here. And then let's set up our variables. So I'll clear sum, and I'll clear I. I don't know if it'll let me use I as a variable, or if that might be a reserved word. So down here at the bottom of my program, I'm going to have some labels. Sum is going to be a word with a value of 0, and I is going to be a word with a value of 0. And at the very end, I'm going to say .end, and I'll put in the starting location. So that when we load this in as a tape, it will start with the PC at, in this case, 1000. Alright, so we've cleared the sum, we've cleared the I. Let's go ahead and make our main loop. So we'll increment register I, we'll add register I to sum. And then I want to do a comparison. And so if I look in my instruction set, there's a compare instruction right here, CMP. It will compare any source to any destination. So I can compare an immediate value with a memory location. So I'm going to say compare I comma immediate value 10, and then I want to do a conditional branch. And so that should be a BNE, branch if not equal, right here, branch if not equal, and I can put in a branch location. So branch if not equal, back to loop. Otherwise, I'm just going to sit here and I'm going to spin in this infinite loop at the position done. I could also do a halt instruction if I wanted. So that's our basic program. Let's see if it assembles. So we'll assemble macro sum1, yes. And I added a little hook on here so that after you assemble something successfully, it creates a file named A, which is a link to the tape file that you just created. Why? So I don't have to keep saying load space sum1.tap. I can just say L space A. And as long as this file doesn't exist or is a link, it will go ahead and replace it. If I have a file called A, it will skip that. So anyway, I've got my program. I can also look at my listing file, but not like that. Right, and I can see the binary that was created as a result of this. I can see that I started location 1000. My sum is at 1040 and my counter is at 1042. So let's go ahead and run our PDP-11 emulator. And I'm just going to say load A, and then I'm going to say continue. And it's sitting here at this address, which looks like 1040. And if I look at my location 1040, that's going to be the instruction right after this branch to done. So while it's executing this branch, the PC is 1040. So it is definitely finished. I can do Control E to get access. And then let's take a look at sum, which was down at location 1040. Examine 1040, and it's equal to 44 octal. I think I can do examine in decimal, and I'll see 36. So that's not the correct sum. That is what 44 octal is, but adding up the numbers 1 through 10 should give me 55, and instead it gave me 36. So something is wrong here. So now we get to debug, right? So I can let's reload. Yeah, I clear these in the beginning, so I can just go ahead and reset my PC to 1000 and start stepping through and see what happens. So I'll set my PC to 1000, and now I can start single stepping. And I'm clearing 1040 and 1042. And again, 1040 is our sum, 1042 is I. So I'll step. And I'll increment, and I'll add, and I'll compare 1042 to 10, and maybe you already know what's going on here, but when I look at this in the assembler, I'm thinking, you know, common world, writing code. When I'm looking at it in the debugger, my brain has shifted gears, and I'm thinking, you know, interacting with the computer mode, and it immediately jumps out to me, hey, this is an octal number. So it's actually adding up the numbers 1 through 8, which is correctly 36. So we found our bug, and instead of adding up through octal 10, we'll add up through octal 12, which is decimal 10. Alright, so we'll reassemble, we'll reload A, we'll say continue, we'll halt, and then we'll examine our sum, which is 1040, and it's 67, and if we examine that in decimal, it's our good old 55. We made a counting program. Alright, so that's you know, kind of illustrative of the development cycle that you follow. And oftentimes you write code and it does not work the first time, and you know, for a longer piece of code you might develop each piece by itself and test it as you develop it, so that when you're done you don't have 10,000 lines of code and it's not working right. Where do I start? But this was a simple enough program that we could start single stepping through and figure out what was happening. And it's really worth, you know, I stress this in my programming tools class, it's really worth setting up your environment in a way that works well for you, so that, for example, you know, I can hotkey from my source code to my assembler tools to my simulator, right? And I'm just using control and an arrow key to go between those. I'm not even touching my mouse. And so I can come in here and I can make my edits, and then when I'm done I can just come back here, hit an up arrow and enter, and it assembles. And if I have, you know, a typo in here, it's like, oh, something went wrong, oh yeah, I shouldn't have that in there. Make that change, reassemble, right? I'm not wasting any time typing in things that you know, open up windows that I have to point and click on and all that kind of stuff. It's all very rapid fire. And then you know, in here just reload your software and you're good to go. There's also a lot that we can do inside the simulation window itself. So for example, I can look at my program in this simulation window. I can do an examine-m and actually see the instructions here, which can help. We can look at, you know, our variables. Well, I reloaded things, but let's go ahead and run. So I can look at 1040, and that's our sum. I can look at 1042, that's our latest value of I, which is 10. And so, you know, ideally, whether you're messing around with retro computing or you're working on a programming assignment for school or whatever, hopefully you've got a tool chain that works well for you. You've got an environment set up that's comfortable for you, and you know, there's a gazillion videos on that elsewhere. Okay, so we've got our basic program for adding up consecutive integers. Let's do the ultimate and generate prime numbers. So when I was a kid, right, it wasn't a machine until I had, you know, used it to generate prime numbers. That's how I learned every new language. That's how I learned every new architecture. It was one of the first programs. So let's play with primes. And so I'm just gonna close this out. Oh, this is also cool. If I hit the power switch, it puts a quick command in there. It doesn't put an enter on it, so I still have the option, but the power switch will, you know, take out the emulator. So here's a really simple prime number algorithm. Let's start off with a equals 1, a equals a plus 2, b equals 1, b equals b plus 2, x equals a over b. If b is greater than x, our number is prime. If x is not equal to integer x, go back up here and try another divisor. Otherwise, it's composite. And we go back up and we try another number. So that's one of the simplest trial division prime number loops that I know of. We don't need to use square root. We don't need to do floating point. If we do a division by integers, it usually gives us an integer value. And so how do we know if x is not equal to integer x? Well, we could also say if b times x is not equal to a. Right? X is a divided by b, so if we multiply x by b, we should get a, unless this x was not exact. In other words, if it was not an integer. On the PDP 1170, the divide instruction is a little more sophisticated than just division. It actually gives you an integer quotient and a remainder. And so this is a double word instruction. I can specify a register and then any source operand that I want. And it will basically take that register, append the following register to it, so it becomes a 32-bit register value, and it divides that by whatever the operand is. And then it puts the remainder into the second register and the quotient into the first. So the setup's going to be, if I take, if I say div r0, comma b, then r0, r1 gets divided by b, and when I'm done, the quotient goes into r0, the remainder goes into r1. And that's all I need. If the remainder is not 0, then I know that x was not an integer quotient. So, so we can wire this up pretty easily in code. Let me move this off to the side, and let's play with prime numbers. So I'm going to grab some stuff here, because that stuff in the beginning is you know, boilerplate stuff now. So, and again, we can do this in the spirit of C program. Oh, I was going to use registers in that sum program. We can do that another time. All right, so so let's start off putting a 1 into A. That's the number we're going to test. And we'll put a label here for new number, which says try a new number. So we'll add 2 to A. Put a 1 into B. That's a possible divisor. Here's our main loop. So that's our next possible divisor. And now we need to do a division, so divide A by B. Alright, so how are we going to do that? We're going to say clear R0, move A comma R1, divide 0 comma B. So this takes R1, R0, treats them as a 32-bit number, and divides by B. And the remainder, remember we said the remainder is going to go into R1. So there's our R1. And the quotient is in R0. Alright, so we've done our division, we're good to go. What else do we have to do? We have to see if b is greater than x. Okay, this will tell us if our number is prime. So, how do we know if b is greater than x? Well, let's compare b with the quotient, which is R0. Alright, so we have all kinds of conditional branches available. Branch if not equal, branch if equal, branch if greater than or equal, branch if greater than, and so on and so forth. So let's do our branch if greater than. So compare b and x. branch of greater than prime. So if b is greater than x prime, if it's not an integer, then we want to go back to a2. So we want to know if it's an integer. Well, that means was the remainder in r1 equal to 0. So we're going to use a test instruction. So we'll say test r1. So is there any remainder? And if it's not an integer, so if it's not equal to 0, there was a remainder, we'll go back to loop. Otherwise, b is not big enough to say that it was prime, but we got no remainder when we divided, so we found a proper divisor, and so we'll say branch back to new num. If we get down here, our number a is prime, and so let's just go ahead and do a halt instruction. And then when we're done, we'll branch back to new num. So we'll get another prime. So a and b are just going to be words, and then there's the end of our program. Let's see how we did. Something went wrong, invalid addressing mode, line 18. So I'll do an 18G, div, maybe it wants an R there. Nope. Let's see. The divide instruction. So the operand goes first, the thing you're dividing, and then the register, the thing that you are dividing into. So the first thing is the thing you're dividing by, and then the thing you want to divide. So this is b comma r0. So divide by b, the number r0. So that should do a divided by b. That works fine. Go ahead and start our emulator. Load our prime. And let's just go for broke. We'll go ahead and continue, and we get a halt instruction. Let's take a look at our listing file. So we stopped at 1064 was our program counter. That's our halt after we found a prime number. And our number A should be at location 1066. So let's examine 1066. That's equal to 3. Let's continue. Examine 1066 is 5. Continue. 1066 is 7. Continue. 1066 jumped up to 13 octal, which is the number 11. So we skipped over 9. Continue. There's 13. Continue. This should skip over 15 to 17. So this looks like it's doing the right thing. It's generating prime numbers. Yay. Let's make it a little more user friendly. So let's display our output in a reasonable way. So I'm going to add a declaration here. I'm going to say LEDs equal 177570. That's where the output register is. So I can display something on my data lights here by pushing it into that location, 177570. So down here where we're prime, before we halt, let's move a comma LEDs 177570. So that should display it. Let's assemble it. Let's load it. And then let's come over here and let's use the continue button. It halts. I'm going to switch this over. Right now we're displaying the address and data from the bus. Let's switch this over to the display register. There's the number 3. If I say continue, there's 5, there's 7. We're looking at it in binary now. There's 8 plus 2 plus 1, that's 11. There's 8 and 4 and 1 is 13, and there's 16 plus 1 is 17. So we've got a prime number generator. Good stuff. Alright, let's throw in one more embellishment just for the sake of, more rapid development. Let's go ahead and specify by ourselves where we want to begin. So it turns out we can also read the front panel switches from the same address. So we can read from 177570 to get the switches. So instead of moving the immediate value 1 into A, let's move the value of the switches into A. And it's going to add 2 to that in the beginning. We're not going to worry about that. Let's go ahead and build this. Let's load it into our prime number tester. So now if I start with a 1 and I say continue, it does R3, R5, R7, R11, R13, and so on and so forth. But if I reload this and I start from, I don't know, let's start from 65 and say continue. The first value we get is 67. That is a prime number. The next one should be 71. Well, that's 64 plus 7. That's 71. Then we should get 73, which is this number here. And then we should jump all the way up to 79 and so on. And remember, we can do all of this through the front panel, right? I don't need to use this handy command line interface if I wanted to generate primes starting with 32769. I can load 32769 into here. Well, let me reset the CPU first. So we want to start from instruction 1000, so there's a 1000. I can say load address, and then when I say start, it should start running from that location. So now I'm going to put in my value that I want to begin calculating from, which is 32769, and if I say start, there's my first prime, right? So 2 to the 15th plus another 3, and if I say continue, it will generate the next prime, and so on and so forth. So now we've got a nice general purpose prime number generator. We can put in a starting value in here, and it will calculate primes from that point forward and display them on the front panel. So of course we can do this in C. Of course we can just go online and say give me a table of primes up to 10,000. But how does that stuff work? Well, this is one way in which that stuff works. Cool. All right, so let me just go back to that sum1 program, and let's get rid of these variables, right? Because if we were writing this in C and compiling it, this might be something like the assembly language that came out. But we have access to registers, so I could just use R0 as our sum and use R1 as our I. Increment I becomes increment R1, and then add R1 comma R0, compare R1 to 10, and if it's not equal, go back to loop. So I don't need those things at the end there. I'm working strictly with the internal registers, and when I'm done, my sum should be in R0. So I can assemble that. Made a typo. That should be a semicolon. So I can assemble that. I can load sum 1. I can say continue. And then when I halt, if I examine R0, that's 67 octal. If I examine it in decimal, it's 55. There's our sum. So even though it's assembly language, it can start to feel, you know, like your favorite high-level language, Python, C, Java, whatever. Once you're in kind of the mindset of what your options are, and especially a CISC machine like a PDP-11, where you have this orthogonal instruction set where you can mix instructions and addressing modes, it's just a super convenient environment to develop in. But you know, it's also really fast. Very small footprint in memory, and pretty fast execution. All right, that's what we've got for this video, and then in the next video I want to start digging more into hardware. So we're going to look at how we can work with some devices on the Unibus, certain areas of memory that are mapped into physical devices. So we'll look at some console I/O, we'll look at the paper tape punch and paper tape reader and the line printer, and then the video after that we'll talk about interrupts and move on from there. All right, thanks. Bye.